Alright, so you know that a power series around x naught is just a summation that looks like this. You add up terms from n equals 0 to infinity of the form some coefficient, a sub n, times x minus x naught to the nth power. It's just like a polynomial that goes on forever. And, one reason that we're concerned with power series is that they can be ways of representing functions. But for now, we just want to think of a power series and consider the following important major property of a power series, which is whether or not the limit as n goes to infinity of the sum up to n exists and is finite. So here's what you're supposed to imagine. Take 10 terms in the power series, add them all up. That gives you something. Then take 20 terms, then take 100 terms, then take 1,000,000 terms. As you go through that limiting process, does the value of the power series settle down to something? Does that limit exist, and is it finite? And if the answer is yes, we say that the power series converges, and if the answer is no, we say that it diverges. All right? And typically, what we may find is that the answer to this depends on the value of x. There typically exists some number r, where r is a positive number, right? It's between 0 and infinity, such that the power series gives you convergence if you're within r of x naught, where again, x naught is the point where the series is centered. So if you're within r of x naught, then you converge, but if you're further away, right, if x minus x naught is greater than r, you diverge. And here, this sort of critical distance r, this critical distance from the point where the power series is centered, that's called the radius of convergence. And then there's this thing called the interval of convergence, which is just the actual values of x that are within the radius of convergence, right? So you think of a value of x, and if x is, no more than r to the left of x naught and no more than r to the right of x naught, then we say it's in the interval of convergence. And, when you took calculus, you might have learned a bunch of different ways to assess power series convergence, but there's one that's most important to me that I want to make sure you know, and it's called the ratio test. So we're going to consider a power series, and now I'm just going to even simplify the notation even more. Here, a sub n, capital A sub n, just represents the entire nth term of the power series. And what the ratio test says is take the ratio of the n plus first term to the nth term, take the absolute value, and then take the limit of that as n goes to infinity. So what you're doing is you're looking way out at the end of the power series, and you're taking the ratio of a term and the previous term, and looking at the absolute value. And we're going to call that L. And if that exists and is finite, then the series converges when L is less than 1, and it diverges for L greater than 1. And I know this might seem abstract right now, so I want to make it concrete with an example right away. As our power series, let's consider the Taylor series for the function 1 over x squared plus 4, centered around the point x equals 0. We're not going to derive that Taylor series here. You can just apply Taylor's formula, but it has the following form. If you turn the crank, it's the sum from n equals 1 to infinity of minus 1 to the n plus 1, x to the 2n minus 2 over 2 to the 2n. So to apply the ratio test, I have to take the limit as n goes to infinity of the absolute value of the ratio of these two successive terms. And so this bit of business here, that's taking the expression here in the power series and substituting n is n plus 1, right? So we have minus 1 to the n plus 1 plus 1, coming from this, times x to the 2 n plus 1 minus 2, divided by 2 to the 2 n plus 1. All right, so that's the numerator of the ratio test. For the denominator, we just take the nth term, and since we're supposed to divide by a sub n, I'm going to multiply by the reciprocal here. So that's 2 to the 2n over minus 1 to the n plus 1, x to the 2n minus 2. And there's a lot of simplification we can do, right? So if we cancel out the 2 to the 2n over 2 to the 2n plus 1 terms, we're left just with a denominator of 2 squared, which is 4. The -1 terms we're just going to ignore because we're operating inside absolute value bars, so they don't matter. And we have x to the 2n plus 1 minus 2 here. We have x to the 2n minus 2 here. And when we simplify, that gives us x squared in the numerator. So I get the limit as n approaches infinity of x squared over 4 equals L. And what the ratio test tells me is that we have convergence when L is less than 1. Well, for L to be less than 1, the absolute value of x has to be less than 2. To have divergence, L is greater than 1, and that means absolute value of x is greater than 2. So therefore, the distance 2 is the critical distance. We say that the radius of convergence is 2, and the interval of convergence, since this is a power series centered around x naught equals 0, we go 2 to the left of 0 and 2 to the right of 0, so the interval of convergence is -2 less than x less than 2. You might be asking what happens with the ratio test when L equals 1, and the answer is it's inconclusive. If L equals 1, the ratio test is not telling you the answer. Alright, let's do one other example. Let's do the Taylor series for f of x equals natural log of x around x naught equals 1. I've written down the power series for you here. It's -1 to the n plus 1 over n times x minus 1 to the n. And I apply the ratio test, so it's the limit as n goes to infinity of this expression here, which is where I've taken this term and substituted n plus 1 for n. And then I'm going to multiply by the reciprocal of a sub n, and that's this term here. All right? So when we simplify, we can again ignore all the powers of -1 because we're inside absolute value bars, and I get n divided by n plus 1, that's this bit here, and then I get x minus 1 to the n plus 1 divided by x minus 1 to the n, that's just x minus 1. Now, here there's a bit of work to do as we take the limit as n goes to infinity. The n's have remained in the expression here, so we have to actually ask ourselves, what is the limit as n goes to infinity of n over n plus 1? Well, it's 1. So this limit simplifies to just absolute value of x minus 1. That's our value of capital L. We're going to have convergence when L is less than 1. That means x is between 0 and 2. We're going to have divergence when L is greater than 1. That means x less than 0 or x greater than 2. So the radius of convergence is 1, and the interval of convergence is x between 0 and 2. That's how you apply the ratio test, but it's very important to me that you understand the significance of convergence and the significance of the interval of convergence. So let's consider estimating the natural log of 1.9, whose true value is written down here, using n terms of the power series from the example we just did. So like you go back up here, you take this formula, and you say, well, I'm just going to add up the first term. Take the very first term of the power series. And if you do, you get the value 0.9. And if you take the first two terms, you get this value here. And if you take 42 terms, you get this value here. And you can see that the value of the power series is sort of settling down. And you can also note that the number 1.9, that's in our interval of convergence. Okay? So as we take more terms, we're converging to the true value of the function natural log at that point. Now look what happens if we just shift our value a little bit. Instead of natural log of 1.9, I'm going to take the natural log of 2.1, whose value is here, and we're going to take the first n terms. So I take the first term, value is 1.1. Okay? Second term, value's 0.495. 40 terms, it's 0.156. We're still not very close to the true value. 41 terms, we're here. As I keep going, 1,000 terms, we're at -1.29 times 10 to the 38th, right? So the point is here, the series isn't even converging. It doesn't even settle down to a value, and we're certainly not doing a good job approximating the value of the function because we're outside of the interval of convergence. That's why this stuff actually matters. All right, thanks for listening.